My name is Victor, and in this video we'll be talking about the basics of CDC static analysis using ALINT-PRO with one of the examples provided in the installation. Today's digital designs use complex architecture with multiple asynchronous clocks, and sending data between asynchronous clock domains can lead to metastability in the receiving domain. This occurs when the incoming data changes during the flip-flop sampling window, and therefore causes a timing violation. So to minimize metastability issues in a design, the clock domain crossing paths must be properly synchronized. CDC, aka clock domain crossing, analysis in ALINT-PRO involves both static and dynamic verification techniques to ensure reliable cross-domain interactions. In this example, we'll talk about CDC static analysis using the CDC Simple Demo workspace, which contains 6 projects. We will also run static CDC analysis on this project using the CDC ruleset. So, let's go ahead and open this sample workspace by double-clicking on it, and you'll notice that we can see our 6 different projects within it, as well as a readme.txt, which holds useful information for this tutorial that I'll be going over, but I won't have it open during the tutorial video, and you can still follow along with it if you'd like. However, before we begin running through each of the individual projects, first, I'm going to clean my workspace just so that everyone's on the same page before we begin. And then the second thing I'm going to do is I need to go over to my tools and preferences in order to customize my policies. Specifically, I want to take a look at the ALDEC_CDC policies and enable just those ones. So, by default, your policy editor might look something like this. And so to disable that, you can just unmark all of your rules, only select the ones we care about, and in this case it's the CDC rule set, and then we can press Ctrl-S on our keyboard to save it to our preferences. You can also, if you'd like, export these policies using the Export Policy File button. However, I've already done that here for the CDC only policy. It saves it as a .do file, which can be run as a script on any of your future workspaces to then apply these policies. So I'm not going to do that since I already have it done. So I'll close out of that, and then we can go ahead and begin with CDC1 initial. So the first thing I'm going to do in order to run this project is I need to select it and set it as the active project. You'll notice at the moment that CDC3 is the active project because it's bolded, but I can set CDC1 now as the active project, and we'll go in order from there. Closing out the Preferences tab, and now I can double-click on the CDC Analysis button here in the Flow Manager. If this does not pop up for you, it may be because you're under the Default tab, so you can switch over to the CDC tab instead. And then all you have to do is double-click CDC Analysis, and it begins the analysis for you over here. So while that's going on, I'm going to go ahead and open up our source code file, so we can take a look at that. And it looks like we have a test module with 2 different clocks, 2 different resets for those clocks, an enable signal for one of the D flip-flops down here, as well as a 4-bit input data and a 4-bit output data. At the moment, you'll notice that we don't have any design constraint file, and that's purposeful so that we can see the full range of going from every step from design entry to clock setup and the rest of these phases, which we'll be going over. So, now that I've gone ahead and done this, I'm going to show a view of what this code has instantiated, or what the tool has instantiated using this code. And I'm going to do that by going over to this design. So I have the test.sv, and I want to show this in the RTL view. There's a few ways to do that. The way I'm going to do it is I'm going to go up here to this toolbar, and you'll notice we have lots of helpful tools. Specifically, I'm going to click on the Open RTL Schematic, and that opens up the RTL view for my CDC1 initial project. So we can see exactly what we have instantiated or synthesized from the source code. And you'll notice we have 3 D flip-flops, 2 of which are for data. One's taking the data in, sending that to another register, and then outputting that data. And you'll also notice that each of these different D flip-flops actually work off of 2 different clocks. One uses clock A, so it's in the domain of clock A, and the other is in the domain of clock B. And if these are asynchronous clocks, then that means that we will have cross-domain crossing issues. As such, this design will need to account for that, assuming that clock A and clock B are asynchronous. And we'll get into that more so in CDC 5 and CDC 6. However, for the first 4 projects, we're going to be mostly talking about the design constraints that you have to add to your ADC file or your design constraint file. So now that we've taken a look at the RTL view, I'm also going to mention a few things about the views on the outside. There are quite a few views on the outside that I have here because they're going to be popping up with useful information as we progress. I'm going to briefly introduce the clocks and resets viewer. I'll go more in depth later once more things pop up into this viewer. But essentially, this just lists all of your clocks and resets, as well as whether or not they're asynchronous or synchronous, and their speeds, or their frequencies. I'll get to the CDC and RDC viewers later, as well as another view. And for the moment, we'll be concerned with the violation viewer. This is going to be the big thing that helps us figure out how to go from one phase to the next. So as you'll notice over on the right-hand side, we actually have a few different measurements for how well we have been succeeding in each of our phases. So like I mentioned, we go through each of these phases sequentially, and we started with the design entry phase, which is the same as the first 3 phases in the default flow manager: parse, elaborate, and synthesize. So you'll notice that's exactly identical to what we have over here. Now, after the design entry phase, we move on to the clock setup phase. And in the clock setup phase, this is where we see all of our constraints for the clock that need to be set up. So if we take a look over in the violation viewer, and you'll notice we missed a critical rule here, we have a violation for a critical rule, the violation viewer is going to list that. And so in this case, it happens to be CDC 3.1, which is essentially dictating that we need to describe our clock with constraints within a constraint file. And we can open this up to see each individual instance of our violations. So you'll notice we have 2 violations because we have 2 different clocks, both of which are unconstrained. And so if you're unsure what each of these violations might mean, or if the description is not clear enough to you, what you can do is you can right-click on it and say Show Rule Description, and that's going to pull it up in this Rule Description viewer, which contains lots of useful information. Information including what this problem is, what that violation means, and why it's important that you don't just ignore the violation and waive it, as well as example codes showing instances where this violation pops up, and then how to fix them. So in this case, you'll notice that we have a sample code with clock A and clock B, and you get the error of the same thing we just got, an unconstrained clock. So that's this message here. And all you have to do is add in a create_clock command into your .adc file, which is mentioned here. You will also have to specify the asynchronous clock groups for each of the clocks, because the tool wants to know if 2 clocks are dependent on each other or independent of each other, whether or not they're asynchronous. And as such, you can implement that using the clock group command. However, we'll see that in just a bit. For the moment, all we want to talk about is, well, hey, now that I know what I need to write, how do I do that? So you go over to your project, and you can right-click, add new file, or an existing file, if you have one, and then you can add in the design constraint file, and you can essentially just copy-paste this code into that file, and just rename your clocks and set your periods as desired. However, instead of having to go through the entire rule description viewer every time you get a violation, occasionally, depending on what phase you're in, the tool will provide you example or suggested constraints to apply to your project. So in your project manager, instead of being in this window, I'm going to move over to the file browser window. And so here I can take a look at the ALINT output folder, followed by the constraints folder, and then the chip level ADC. So close to the bottom of this file, well, in the top you're going to have the constraints that you currently have listed in your ADC file, but at the moment there aren't any. So instead, what we're going to be concerned with are these suggested constraints. So what we can do is we can take these instead, without having to look at the rule description viewer, and apply them to our design. And you'll notice you see the asynchronous clock groups down here at the bottom. And we are going to have clock A and clock B in this project be asynchronous clocks. And they're actually going to have different periods as well. The first will be a period of 10, and the second will be a period of 2. So with that in mind, you would just take those lines of code, you would make your ADC file, and throw those lines of code in there, and then you would rerun your CDC analysis step by double-clicking on this button here. So the next thing we'll be doing is moving on to the second project in this workspace. So again, what I'm going to do is I'm going to right-click on this project and say Set Project as Active, so that I've selected this as my active project. And you'll actually notice that all of my viewers have now updated, as well as the Flow Manager, to reflect that I actually haven't done anything with this design yet, since I cleaned it at the very beginning. I will also, while I'm running this CDC analysis by double-clicking, I'm also going to take a look at the differences between both of my implementations. So, closing out some of these tabs, I can take a look at the differences between the source code files, and you'll actually notice there aren't any, because the only thing we've done here is we've included the test.adc file for our design constraints. And here, exactly as I mentioned before, are the create clock commands for the external clocks, essentially declaring them, with 2 different periods. But I also have my asynchronous clock groups to specify that these 2 are in different clock domains. You'll also notice that our clocks and resets viewer has been updated to specify these clocks and their frequencies, as well as the violation viewer has now been updated to show your new violations. And you'll also notice that the clock setup phase is complete. It's listed as green. We've correctly implemented all of the critical rules, and we haven't violated any non-critical rules either, since we have 100% quality. And so now we're moving on to the inputs and outputs setup phase, which this, like the clock setup phase and also the reset setup phase, all have to deal with just adding constraints to your ADC file. And so that's what we're going to be doing for the majority of these first few steps. So taking a look at the violation viewer, you'll notice that we have violation 3.6, specify delays for top-level ports. And so that's essentially just saying, hey, these signals are from clock domains, and we want to know what the delay is with respect to those clocks. So for example, DIN and DOUT, or DIN is from clock domain A, enable could be from clock domain A, DOUT gets output on clock domain B, and maybe these are from neither, these are asynchronous. So we need to know how to take care of that. So again, all you'd really have to do is you'd say, okay, show my rule description, go over to the rule description viewer, and you can read through the problem description and see what it mentions. At the moment, though, you'll notice that this is for 3.6 instead of 3.1 like it was before. And you can also, if you have multiple different violations, click on them, and that'll switch between the 2 different rule descriptions instead of having to right-click every time. So we can go over here to the bottom, and we can take a look at all of the different files that we have to add in, specifically the constraints set input and set output delay, as well as some setting of false paths. So if we go all the way to the bottom, we can see some examples where we set some false paths. So these set input delays and set output delays are for the signals which are synchronized with respect to a clock or from those domains. And the set false paths are just for your asynchronous signals. So we would, again, just copy-paste that over into our .adc file, or we could go over to, again, our file browser, over to the chip-level ADC file, and we can take a look at our suggested constraints, and we can see exactly what we mentioned. We have DIN being related to clock A, we have enable being related to clock B, and we have DOUT being related to clock P, so those were all mentioned to us earlier. And we also have our false paths for reset A and reset B. So these suggested constraints are really helpful in saving you time, so you don't have to go look up every single violation if you don't need to. So you would then take this, put it into your .adc file, and then we could go ahead and run the next step. And so that next step is going to be covering the reset setups that we're gonna be looking at, and that'll be over here in CDC 3. So we have the exact same deal here. We go ahead and right-click, set this as our active project, and I'm going to go ahead and run the CDC analysis. And while that's happening, we can start by comparing our test.sv files. So here I have the 2 files, and again, there's no change in the source code. The only change going from the previous one to CDC3 is what I mentioned about the setup for the inputs and output delays, as well as setting our false paths for our asynchronous resets. And so that's the only major difference, going from 2 to 3. And so now we can analyze the new things that have occurred on each of our viewers, as well as the new things we need to fix based off of our violation viewer. So let's go over to the clocks and resets viewer, and we can see that we actually do have the unconstrained resets. So we have reset A and reset B listed as asynchronous resets, so those have been added in. And then for our violation viewer, you'll notice that we actually have 2 different critical warnings, which are that each reset needs to be described with constraints, specifically reset A and reset B. And this is identical to what we were looking at before when we were asked to describe clocks with constraints and also with the inputs and outputs. So again, we can right click, say I want to look at that rule description, read up about it, see why it's important, and then we can take a look at examples to create those different sets of commands in the .adc files. And then we can either use them in these templates to put into our .adc file, or we can go over to the file browser, ALINT output, constraints, chip level ADC, all the way to the bottom here. You see, okay, we have those create resets. So we can take these, put them over in the test.adc, and that's pretty much it for this warning here for 3.2. Now, if we go back over to the project manager, the next step we're going to be going on to is CDC4. So after this step, we will have finished reset setup, and we're going to begin on structural CDC and RDC, which is where we're going to see actual differences between the sets of source code. So let's go ahead and go over to this one and begin on that. So again, I'm going to go ahead and right click on this, set it as my active project, and then I can begin the CDC analysis. So when this occurs, while this occurs, we're going to take a look at the differences between this project and the previous one very quickly. So you'll notice that going from CDC3 to CDC4, all we did, like I mentioned before, is adding in those create reset commands. So I can close those out, and I can also take a look at the changes in the source code. Now, in the source code, you'll notice that there are no differences. However, after CDC4, there will become differences in the source code in CDC5 and 6. So I'll go ahead and leave that one open. And now we can take a look at the differences in all of our viewers going around. And we'll also notice that we've made it past the clock, input outputs, and reset setup phases, and we're into the actual structural CDC and RDC phase. So starting from the top here, we have the CDC viewer, which also corresponds to the CDC schematic window. Both of these have related information. So I'll go over the CDC schematic first. So I'll go ahead and zoom out here and open up these domains so we can take a look inside of them. Fit that, zoom out a little bit more. There we go. So the CDC schematic window contains blocks for each clock domain, and it has the connections that are between each of those clock domains, and those connections also indicate how many paths there are coming in and going out. Additionally, within each clock domain, the crossings from block actually contains all of the CDC paths sent from this domain to another, whereas the crossings to block, which you see over here, contains all the CDC paths received by this domain that are coming from another. Additionally, the crossings to block will hold the combinational logic and synchronizers that are on your CDC path. So later on, when we get into CDC 6, we'll be noticing that we can actually see a synchronizer here within the crossings to block. Now, the information presented in the CDC viewer is similar to the information presented in the CDC schematic. However, the only difference is the way it's presented. So mainly here it's presented in this tree format where you can click on each of these arrows and essentially show what each of the crossings have, what signals they correspond to, as well as, pretty importantly, details about their synchronization scheme. So in this example, you'll notice that we actually haven't synchronized any of our signals. And so that's a big problem, which we'll be getting into later. Closing all of those up, the clocks and resets viewer hasn't changed that much. The only difference is that I have both the clocks and the resets open for viewing. all these are going to show is simply the path of this clock throughout each of my designs. Closing that up, we can now take a look at the RDC viewer, which is similar to the CDC viewer, except it's specifically for reset domains instead of for clock domains. So it shows design reset domains, and it also shows any clocks and resets within those domains. So for example, the reset A reset domain has clock A and reset A, and the reset B domain has clock B and reset B. So we can go ahead and close those up, and now we can actually take a look at the violations that we've incurred. So taking a look at the violations, we have 1.1, which essentially states that we need a synchronization circuit to transfer data between two asynchronous domains. And then we have the next violation, 1.10, which says that if we have an asynchronous reset, we need to use a reset synchronizer in order to use it. And finally, we have violation 1.11, which is essentially saying that we need a synchronization circuit for any external signals that are asynchronous. So, keeping all of that in mind, the first thing we're going to tackle is the 1.10 violation. So we can right-click on this and show the rule description and read about what this violation is saying. And essentially, if you were to read through this, you'll notice that essentially if the active clock edge occurs at the same time that your reset, or if it was a set signal as well, as at the time that deasserts, you get a possibility for metastability if those occur at the exact same time. And so you need to ensure that your reset is not going to deassert at the exact same time that you receive an active clock edge. And so you need some sort of synchronization circuit. You could also, if you wanted to, and it's detailed within this document, instead of putting in an actual synchronization circuit, you can specify it within the .adc file, essentially saying that externally you've handled the reset synchronization and it's not present in your design, but the tool shouldn't worry about it because it's already handled. However, in the case of this program, we actually do have a reset synchronizer added in. And so what we can do is, like I mentioned, we could look at examples of reset synchronizers in 1.10. And we can look at when these examples pop up and when we need to fix them. So in this sample code over here, we have a asynchronous reset signal that we need to worry about and we need to synchronize. And so they fix that code by taking in that reset signal. And down here, you'll notice that they actually have some synchronization flip-flops. So these two flip-flops are going to take in the ARST, which is the asynchronous reset, and it's going to run it through a 2D flip-flop synchronizer, also known as a brute force synchronizer. And then you can use that reset as a synchronous reset for whatever it is you're trying to reset. Now, we can also take a look at the next project in this stage and see how it is they implemented it. And you'll notice they actually have a separate file for that reset synchronizer. Now, before I actually go to that, I do want to open up my RTL view here, just for the sake of comparison, because I want to see what exactly has changed when we look at the two different RTL views. So now we can move over to CDC5, which has this one new file, which we expect to have the reset synchronizer, and possibly some changes in the source code for test.sv. So let's find out. So let's go ahead and right-click on this and set it as our active project. So now that it's our active project, we can go ahead and go over to the flow manager, run CDC Analysis, and once we go through that, we can take a look at all of the differences. Specifically, we can start with the RTL view differences, because we're going to see, hopefully, that reset synchronizer somewhere inside of our design. So we finished up, and I can go ahead and press the RTL schematic view, and you'll notice that's exactly what we have here. So you'll notice that the 2D flip-flops still are identical, as is the enable stable flip-flop. So all of these are still here, but the only difference is that we have a reset gen module here, which is an instantiation of our reset synchronizer. And all this is doing is it's taking in the clock A and B, as well as reset A and B, and then outputting reset A and B, but synchronized. So there actually was no change over to these green blocks and the way that they're connected up. The only difference we've made is instead of connecting the asynchronous reset signals RSTA and RSTB, we've synchronized them and then sent those reset signals instead. So with that in mind, we can also take a little bit of a look inside of this reset generator, and you'll notice that we actually have a 2D flip-flop synchronizer for each of these resets. So here we have a 2D flip-flop synchronizer for RSTA, and then one for RSTB. So that out of the way, now we can also take a look at any differences in the CDC, the view for the reset constraints. So if I go over to, or sorry, not the reset constraints, the CDC schematic, I can open that up, and we can see if there are any interesting things we can find in this. So you'll notice that we don't have any big differences. This is identical to what we saw before. However, if we go over to the RDC viewer, you'll notice that we have now two resets labeled for our reset domains. So we have RSTA and also RSTA sync. Additionally, for RSTB, we have just the regular RSTB and RSTB sync. So no differences in the clock domains themselves, because all we've done is add a reset synchronizer. Let's go ahead and close this, as well as the RTL view for this one, and the previous test.sv file. And looking through all of our views, you'll notice, like I mentioned, they all seem very similar. So we'll go ahead and move on to talking about the violation viewer, which here you'll notice has mentioned that we don't have a 1.10 error anymore. So that warning, that critical warning that was a violation, is now gone because we've added in that reset synchronizer. And so now all we really have to do is focus on how to fix the very last issue. So this issue here is going to be solved just by adding in one synchronizer. And we can go ahead and, if we wanted to, take a look at each of these and see what they're affecting. But you'll notice for all of these, we have D0, D1, D2, D3, as well as your enable stable signal. So keeping that in mind, this all has to do with the exact same spot in our RTL schematic. It's mentioning this D flip-flop here. So we need to make sure that we have this D flip-flop synchronized. Now, in order to do that, what we're going to implement is an enable synchronizer. So this right here is going to be replaced with two back-to-back D flip-flops, which then will provide a clean enable signal to then be sent to this D out register, which is an enable synchronizer. Now, the enable synchronizer is a type of synchronizer recognized by the ALINT-PRO tool, and when we actually implement it, we will be able to see it within this view, within the CDC schematic view. Now, keeping that in mind, we can go ahead and take a look at some of the differences in the source code, and then we'll move on to CDC6. So, really quickly, to get the .adc file out of the way, there are no differences in constraints. And for the test.sv file, the main differences here are that we've simply instantiated this reset generator, and that instead of feeding the reset A and B to each of these flip-flops, we're instead feeding reset A synchronized and reset B synchronized. Everything else is identical, however. So those are the only changes. And finally, we can also take a look at the reset synchronizer module and see how they made it. And again, this is what I described before in this diagram, where you see the two back-to-back D flip-flop synchronizers, and these are both of them there, one for clock A and one for clock B. So I'll go ahead and close out this tab. We'll keep this open as well as the view of our RTL, and we can use these to compare when we switch over to CDC6. So going ahead, right-clicking on CDC6 and setting this as our active project, we can again run CDC Analysis, and this is going to be the last time we're doing it for this tutorial, because at the very end, we're going to see that our structural CDC and RDC phase passes successfully, and we can take a look at all the differences that have been found in each of our viewers. So you'll notice, there we go, our CDC analysis is finished, And we've successfully completed every phase with 100% quality, no violating any of the critical rules. So the first thing I'm going to do is I'm going to take a look at the difference between the two sets of code. So for example, between the .adc files, there is no difference. We can take a look at the reset synchronizer files, but again, there is no difference. However, if we take a look at the test.sv files, and we take a look at the difference between these two, it might be a little bit difficult to see, but down here in this flip-flop, we actually have it replaced with a two back-to-back D flip-flops. And so this is going to create our enable signal, which is going to make our enable synchronizer. That's going to be fed in to the second 4-input D flip-flop. So if we go ahead and actually open up the RTL view for this project, we'll be able to see that. And so here you'll notice the main difference between CDC5 and CDC6 is we have an extra flip-flop here, which essentially stabilizes the enable signal because it's coming in from clock A's domain, and we're synchronizing it to clock B. So we send it to a 2D flip-flop synchronizer, and then that enable signal acts as an enable for this D flip-flop 4 register, which is going to be an enable synchronizer for this system connecting between these two. So we kind of have two synchronizers here, one for the enable signal itself, and then overall that forms an enable synchronizer. So with that in mind, we can also take a look at the differences with this window here. So I can go ahead and click on the CDC schematic window, and I can open it up. So bringing it over here, we'll notice that we can open both of these up. So I'll go ahead and open up the old one first. Zooming all the way out, we can open up the important part, which is this right-hand side, the crossings to domain. But I'll also go ahead and open up the crossings from domain. And then we can compare that to CDC6. So opening this one up, you'll notice as we go into this last one here, we can actually see our enable synchronizer that's been recognized by ALINT. Opening up, however, on the left side, we don't see any differences. So this goes back to, as I mentioned close to the beginning of this video, that the ALINT-PRO software is able to recognize different types of synchronizers. Now, in this case, it actually recognizes our enable synchronizer, which could also be called a wide enable. We'll see that in a little bit. And then we can open this up to see where exactly that synchronizer is. So here we have those two enable flip-flops, and then we have that leading into the enable signal, or the enable port for our D out register, and that forms our enable synchronizer. So those are the differences in this view as well as in the RTL view. And now we can go ahead and close those out and take a look at the last few windows to see what the differences have been. So taking a look at the CDC viewer, you'll notice we can open up the domains and we'll see many of the crossings between the two. And very importantly, we'll be able to see exactly how those crossings are handled. Remember before, these mainly said not synchronized. However, at this stage, each of these have been synchronized. Some by the wide enable or the enable synchronizer, and one by a ND flip-flop, or in this case a 2D flip-flop synchronizer, also known as a brute force synchronizer. And crossings from the asynchronous domain are mentioned as being synchronized by the reset. We can also look at domain 1, but this is just going to contain the same crossings, just instead of saying from, they'll be saying to. However, it's the exact same information. And we could also look at the asynchronous crossings, which mention the resets and their synchronizations. Closing all of that up, we can take a look at the clocks and resets viewer. Not too many differences here, though we do list more spaces where each of our clock signals goes, because if you recall, we added in more hardware to the reset synchronizer, which uses the clock signals, which is why you have so many pins here. However, that's the main difference for the clocks and resets viewer. For the RDC viewer, we can again take a look at all the clocks, the resets, but this hasn't changed all that much. And if we were to look at the non-resettable domain, we see clock B in there. The most important part, and the best part about this particular project here, is that we've actually gotten through all of our violations in the CDC design, and you'll notice that that pops up here in the violation viewer as having no more violations. So excellent work. Now we've finished up all of these, and we've gone through every single project step by step, explaining along the way how to go about solving each of the issues with the violations, how to go from one violation on your violation view to finding out what that violation describes, how to then apply that to your design and solve it. So, that's all for this video. Thank you for watching.